Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, we have in a previous video we did actually deadlock avoidance, and we saw that if we have a resource with single instance, then we're going to use the resource allocation graph. But if we have multiple resources, say we got a printer with 3 resources, disks, 4 disks, 5 printers, and so on, so then resource allocation graph is not going to work. So in that case, we're going to use the banker's algorithm. Okay, in in a RSA, we also need the a priori information in the banker's algorithm. Okay, so the banker's algorithm is a resource allocation and deadlock avoidance algorithm. It was developed by the Dijkstra and for the operating system. Okay, also it's called as EWD 108. Okay, and in this algorithm we also check what's called as the safety. Okay, we apply the safety algorithm, which what does that mean is we're gonna see before we grant the request, we're gonna see if the system is safe or not. So what we do is we tentatively grant the resources for a request. So basically we are not actually granting the request, we just tentatively or pretend that we have granted the request, and after that we just see if our system by granting that request is in a safe or not. If it is not safe, we just undo that tentative grant. Okay, we block the request process until it is safe to grant, or if it is safe, then we grant the request. Okay, so what we are saying technically is we have a process, say P0, P1 and P2. Now they may have some resources and they may need some more resources, so that's why we need to have an a priori information about the max what every process may need. Now this max is not going to be it is going to be matrix now. Okay, so where basically we will have how many resources P0 may need. Okay, I will show you in an example and you understand properly. And then there will be also the how many are allocated resources are allocated to these and how many are still they can request. Okay, because we need to know a priori that how what is the total requirement of, for example, P0. Say for example it needs 3 printers or 3 disks, 1 printer, okay, and something else more. Okay, or maybe memory, maybe it needs a memory block. Now how many of disks, how many process printers and how many memory blocks it need, so that will be the maximum, and out of them we may have given something to it. Maybe out of 3 disks, 2 disks are already allocated, printer is not yet allocated, and no memory is allocated, or 1 memory block is allocated, or this may be some shared variable which we are trying to access, and so on. And so if we say in terms of A, B, C, what are the resources they are, say P0 is allocated to A resource, 0B, 0C, for example, and the maximum it needs is, for example, from ABC it may need say 4 to 3. Now out of 4, A is allotted 2, so it needs 2. Okay, so requirement is of ABC is 2, 2 and 3, because this is not allocated. So now say for example now for the B, it has not allocated yet anything. Now it may act, the P0 may request 1B. Okay, 1 resource B, 1 instance of a resource B. So the algorithm of our banker's algorithm do what? It actually pretends that okay, I have given it. So, okay, so the situation will be like this. Now with this status, it will try to see whether our system is in a safe state or not. A safe state means, we know that from previous video also, that we should have some sequence of processes so that all processes finish. Okay, it should not stuck, there should not be deadlock and all. Okay, so, maybe the P0 has to wait a while, then P1 may go for first, it will finish, and then P2, and then maybe P0. So some sequence should be there so that all the processes should finish. That's called a safe state. Okay, Now, is by allocating this resource, is our system in a safe zone or not? Okay, that is what a banker's algorithm see. It's called a banker's algorithm because we in a banker's account, we just put up the liquidity constraints. What does that mean is we don't want to give all cash out to a particular customer, so that but others will starve. So we want to have enough cash so that at least all customers get some kind of cash, so that nobody will complain. Okay, from that scenario, we call it as a banker's algorithm. Okay, so for a banker's algorithm to work, we gotta know three things. First, how much of each resource each process could possibly request, that is the maximum, what I was talking about, and how much each resource each process is currently holding, so how much is allocated. Okay, and how much each resource system has available, and how much is available. Okay, so what does that mean is, for example, ABC, we have three resources. Say a process at the max needs 3, 2, and 4, for example. For C, 4 instances of C, 2 instances of B, and 3 instances of A. Now, this is the max, and out of these we may have allocated, say for example, 3A, 0B, and 2C. Okay, A wise it is done. It needs more B in 2 instances of B, and 2 instances of C is still required. But we have to see what we have in hand, because we may have our resources, whatever the resources we have. Say for example, we have 12 A's, okay, 5 B's, and 10 C's. So this much is in totality we have. Okay, out of them we may have given to some processes, for process P1, P2, and so on. Maybe this time around I have in A, I have 1A, 2B, and 1C. This is left out. This is what I have right now, which I can allocate. Okay, so this is what's called as the system, the resources the system is available. So how much is available? Okay, so this may call as available. Okay, and the resources which you talked about are like memory, like semaphores, like interfaces. Okay, and so on. Maybe the disk, or maybe the printers, and so on as well. I think we should take up an example, and by that example we clearly understand the banker's algorithm. Before that, we should need to know what data structures about, because we need to have some data structures which will have this kind of information. Okay, which we need to have a priori, and then we can work with that data structure to see whether a system is safe or not. So if we say, firstly, before that, I would like to sum up this thing that I'm saying. Some process, so PFI, has some request. Okay, it requests, I will say it requests some resource, and our banker's algorithm, this is my banker's algo, it does what? It says, okay, I am done, I will give you that resource. It pretends, it actually doesn't give, it pretends, and it pretends in the terms of data structures. It updates data structure as if he has given that resource to the P of I. Okay, then after that it will check for safety, so it will apply safety algo. Okay, it will apply the safety algo. By safety algo, what we do is we try to see if, after giving this, whatever resources we are left with. Now for example, here we have this much resource, and if we give a particular resource to the process, now there may be whatever we have left out. With that left out, is it possible that all other processes will finish? Okay, if that is so, if our system is safe, okay, I will say system safe. If system is safe, it will go here. If I say yes, system is safe, then I got to, this I just pretended allocation. Now here I allocate. But if I say no, the system is not safe if I allocate this, so I gotta deny it. So I deny, I don't allocate that resource to that process. Okay, now let us this is the sum up of the algo. Now let's work out with the data structure first, then take up an example and master it. So here is our data structure for the banker's algorithm. because we need on one side we may have some processes. Say for example we have P0, P1 and P2, three processes, and say for example we have three resource types A, B, C. Now how many P0 is at the max, what P0 need, how many of A's P0 need, how many of B's, and how many C I need. So I can't have just vector, because that vector can hold only the P0, but I need other guys also, so I need a matrix, simple as it is. So if I have n processes and I have m resource types, number of resource types, okay, for example here 3, so I'm gonna have n cross m matrix. That would tell me how many, for example P0 can at the max P0 needs of A resource, say for example it needs a 10 A resource and 5 B resources and 3 C resources, for example. Now this is the status for the n, that it needs at the max. So maximum P0 needs the instance of A. A may be the printer or a disk or some memory location or something else, memory block, whatever it is, that resource which a P0 needs, or a file maybe, or something else, okay, is 10. Okay, and P0 needs B type, it needs 5, and C type it needs 3. Same with these guys. Okay, so we need to have a matrix, okay, n cross m matrix. That's what available max means here, n cross m matrix. Okay, and now this is the max, and it is a matrix I comma j. I will tell the which row, and j will tell which column. Okay, say for example this is 0 0 0 1 0 2, this is 0 this is, sorry, 1 0, this is 1 1, this is 1 2. So if I'm talking about 1 2 for example, so that means max of 1 comma 2, that is I is 1, j is 2. So what does that what will that tell us? That will tell us how many resources of the C that P1 will require. Okay, so if we say if max of ij is equal to k, that means because if I say 1 2 is, say for example 12, that means P1 needs 12 C resources. Okay, that's what I say, that the PI may request at most k instances of resource type R j, because j will tell us which resource and I will tell us which process. Okay, simple as it is. Now out of them we may have also allocated, we may have allocated our like this same way. We have the processes P0, P1 and P2, and we may have, out of whatever the requirement was, A, B, C, because we had 10 requirement of P0, maybe 5 is already allocated. For B, say for example 2 is allocated, and maybe C is fully allocated 3. The P0 has already attained 5 of A instances of A, 2 instances of B, and 3 instances of C, and so on. Okay, now this is my allocation matrix, which will tell me how many are allocated, and if I then see the max matrix and allocation matrix, I can figure out how many are required. Okay, how many is needed, for example. Does it make sense? So allocation matrix again need to be n into m matrix. Okay, number of processes versus number of resources. And again, if I talk about particular box, that means allocation of I and j, I will tell me which process and j will tell me which resource, and whatever inside is, it will tell me how many is how many instances are actually allocated. Okay, and we may have some vectors also. For example, available is my vector. So available is like this thing, so it will have A, B and C. So this is my available, which will tell me how many A's are available right now. Maybe out of the total we may have total A's. So if I say I have total 10 A's, say 10 B's and 10 C's, for example, this is my total. Out of them, what is available right now, because I may have assigned out of these to these processes, so maybe the left out, whatever the left out is, maybe say so 2, 5 and 5, for example, this scenario. So that means I have already allocated 8 A resources to some processes, 5 B and 5 C resources, because our total was 10 10 10. Okay, so this available I need, it's a vector, it's an kind of an array which will tell me that how many resources I have right now with the system, which is not allocated. Okay, then I also have a need, so it's also going to be the matrix. So need is also going to be the matrix like these, which is actually the subtraction of these two. So if 10 is the maximum required and 5 is given, so need will have 5 in that place. Okay, and I need here b 5 I need, and 2 are given, so there will be 3 in this place. So the need again is going to be the n cross m matrix. Okay, because I have p0, p1, p2, so on, and I got a, b, and c. Now how many is so I have a 5, this minus this. Okay, max minus allocation matrix. So 10 minus 5, that is 5, 5 minus 2, that is 3, 3 minus 3, that is 0. So that means this is the requirement for the p0, that I need these much more. So that's why we are saying here that need of ij is equal to actually max of ij minus allocation of ij. This is just straightforward, because need is what is more required. Now max is the total you need, you want. Allocation is what you got, actually you're holding these things, and whatever is left out is what you need. Simple as it is. You can see this data structure and example from the Dragon book, where you can actually read a little bit of text. Maybe that will also help. Okay, or if you read sideways and watch this video, that will really help. Now let's try to work out with the algo first. Okay, we say this is my algorithm, the banker's algorithm. Okay, this is how I do. This is step first. We firstly say if a request of I, when I say a request of I, okay, in a subscript, when I say request of I, what does that mean? It is a vector instruction. Okay, we should understand that the I here is the row. Okay, it's like available in a vector, which is a complete single row in an array. Similarly here, if I say request of I to tell me the full A, B, C, what is my request? So when a process is requesting the ith process, I must say P0, P1 or P2 process is say requesting, it's requesting like I need 2 A's, 0 B's and 3 C's, like this. So this request of I is a vector which actually tells the whole row. Okay, so I am saying firstly what my algorithms here, what my here are, let's say this is my max, this is the data structure I'm talking about, this is the allocation. Okay, this is my allocation, this is the max, and this is the I guess this is the need. Okay, this is the need matrix. Okay, this is total, this is what is allocated, and this one is what is required. Okay, now if I say if request of I is less than or equal to need of I, so what does that mean? That what I'm requesting say this much I'm requesting, and that is less than or equal to need of I. So whatever I need is if it is less than that or equal to that, so I say okay, that's good, because this is permitted, because my need is this. Maybe some error occurs and I'm gonna ask for 6 A's, 4 B's and 1 C, but I'm seeing my need is not that much. Okay, I already see my need is only 5 A's and I'm asking for 6 A's, and my need is only 3 B's and I'm asking for 4 B's. I am done with the C, but I'm still asking 1 C, or some other scenario where my request, this is the request, is greater than my need. That means some error has occurred, isn't it? Okay, so if my request is lesser than the need or equal to need, okay, I'm asking for 530, maybe I'm asking for 530 exactly, that is my request is same as the need. Okay, so need of I and request of I, I'm talking about vectors which talk about the whole rows, and then it's okay. Then what you should do in this case, if it is true, then I should say go to step second. Then I go to the step second. Okay, But maybe this is not, maybe some error has occurred. Then I must say that you got to generate some error, right? So I may say generate error. If that is not so, that means what I'm asking for is not what I need, so there is some definitely some error. So in step second, if that is so, if what I'm requesting is not like this, I'm requesting like this, and it is in accordance to my need, okay, then I should go further in the algo. But before I can, okay, I will say, okay, I have a 203 requirement right now. In totality, I need 530. If I'm having 530, I can't have this here. That is then the wrong, that's the else part. It should block it. Maybe this is the scenario 200. So I need 2A, 0B, 0Cs right now. Okay, this is my request of I, and it is in accordance to the need. Okay, now before I can go further, I gotta see whether I have this much of A's available or not, because I got an available vector here. Here is my available vector, right, which is telling me about how many A's, how many B's, and how many C's are there. Maybe the scenario is like this. Say I need 5 A's. I'm asking for 5 A's. Okay, before doing anything, I gotta see, do I have the 5 A's right now with the system, because only 2 A's are left out. So can I process this request? I have to see that thing here. So in a step second, I'm gonna see if my whatever I'm requesting I is less than or equal to whatever is available to me, whatever available I is. If we have available the vector available, if that is less than, if my request is less than what is available or even equal to, that means I can have all those things. Then I can go to then here after this. Okay, then what you got to go is go to step second, go to step third. You can go to step third. Else, okay, else what are you gonna do? Is this an error? No, this is not an error. Rather, we should wait, because if I'm asking for 5 A's, which I need, okay, but right now there is available is not that much. This is available, only 2 A's are available, so I can't have the 5 A's. But that doesn't mean end of the world, because some process which are holding the A's may finish and release those A's, and then this available will show that I gotta have maybe some process was holding the 5 A's that will release it. Okay, like P0 is holding the 5 A's, maybe P1 is also holding the 5 A's. Maybe if P1 is finished here, it will release it. So at that time my A count will be 7. Is it? So in that scenario, now this process P0 can be can have those A's, because now we have 7 A's left. So in this case, if I don't right now, my request is not met what the availability is, then I should wait. Okay, then I wait. Is it? Does it make sense? Okay, now if from 1 and 2 you go to the step third, if there was no error, okay, and you don't have to wait, that means whatever you are asking is in accordance to your need. You are not erroneously saying something which is more than your need, and whatever you are requesting is in accordance to what availability is. Then I'm gonna go to step third. That means I should give it. I should give the resources to the process. But Banker's algorithm does what? It pretends. So it pretends in steps third. It pretends allocation. Okay, it doesn't allocate actually. It pretends allocation. So allocation means what? When it allocates, okay, so firstly the allocation I equals whatever the allocation I is plus request I. What does that mean? That means here in our case scenario, that I'm saying that my allocation was this thing 5 to 3. Say for example I was asking for 200, and I have, for example, in this time, in a time frame, I have 755 available. This is in accordance to my firstly my request of I is less than this the need of I, and my request of I is also less than the available, so I can go forward, okay, and allocate it. So when I allocate it, basically my max will have no change, but my allocation vector will have change. Now allocation is not 5, I have given more 2, that is 7. It will update to the 7. That means I have got a 7 A's now. Okay, so when I have allocated 7, that means I have given 2 A's to the allocation, so I have to change this data structure available also. I don't have now 7, I have only 5 left. Let me change my pen, so that will have some effect. Okay, now I am having only 5 left here, right? Let me be more darker. Okay, so I have only 5 left now, so that means my available vector is also going to change, is it? And my need is also going to change, because now I needed 5 A's, now being 2 are allocated, so now it's lesser, so I will minus 2 it, so it will be 3, right? So I have the need vector, the need of I. This need is a matrix. In this I will have an instruction, the vector instruction, where I will say need of I is equal to need of I minus the request of I, and same will be with the available, and with the allocation matrix it will be plus. Does it make sense? So here in a third, I am pretending, not actually allocating. Okay, I'm saying okay, allocation I is equal to allocation I plus request of I, because I got to reverse it if the system is not safe. That is my next phase. So before that I will update my data structure. So I say allocation, and with the available, what will happen with the available? Because available is going to be lesser now. That is what is available minus request of I, is it? What about the need? My need of I is going to be whatever the need was minus the request of I. Does it make sense? So I'm going to do these changes to my system. When I'm done with this, I got to see whether I should make it permanent or not. Should I make this permanent or not? It depends upon the safety algo. So I have to run now the safety algorithm, which will check actually with this scenario, is my system safe? What does the system safe means? That all processes with some sequence should finish. Okay, so we're gonna run what's called as a safety algorithm, which will actually check whether our system is safe or not. So here I have additional 2 local data structures. So in a safety algorithm I got some local data structures. Okay, one is called the work. Okay, it's again a vector. It will be same size whatever the available is. Okay, that means available was how many processes we have. That we have the m processes, so its size will be 1 to m. Okay, and I also want to have another Boolean vector again, but it's about the processes, how many processes we have. Okay, and this is a Boolean. It will be initialized to all false, and this guy will be initialized to the what is available. So whatever available is, I'm gonna put that into the work. Okay, so I am saying the work of I equals to work is equal to, I don't say I here because it's only single variable. It will be for all processes, so I should not use the I with the work or with the available, because available vector is whatever is available. How many A's, how many B, and how many C are available. It is not with particular process but with all process, a global variable. Okay, say for example I got 5 A's, 3 B's, and 2 C's left out. So whatever is that, I put that into the work. Okay, so work is having same thing what available is, and finish is actually all finish variables are true. So this will be equal to how many processes we have. Okay, so all sorry, there will be all false in the beginning. It will be all false. That means no process is yet finished. You have to check if all the processes can finish with whatever resources we have right now. Okay, after allocating, after pretending allocation, we'll see whatever resources we have. With that resources in hand, will all the processes in some sequence finish or not? Okay, so I gotta see I gotta see you know which process can finish. I gotta see all processes which can finish with these resources in hand. Let me show an example, and you will actually understand properly. This is my safety algorithm. Actually, let us first see this thing to understand it. You can see it from the Dragon book. Okay, and what I'm saying is this is available. Okay, okay. Now this thing I will put up in the work. So work will have same 332 scenario, right? Now I will see if I have 332, which process out of these, this is my max. Okay, this is allocation. um, so I need to see the need also. Okay, now this is the need. Okay, um, available is 332. Now that's my work. Okay, and I also have a finish, which is a boolean with every process p0, p1, p2 and p3. So this will actually be initially all false. I should write it outside p0, p1, p2, p3. Now this is the finish vector, which will have false in it will have false initially everything, and work will hold whatever is available. Now what safety algorithm will do is, now this is the available vector after we have pretended location. Okay, now we see if we have this much available, is there a safe sequence or not. So I can see so I start from the p0, I start a loop from the p0 and try to see if the need of the p0 is lesser or equal to the work, but that's not in this case. So I can't allocate 332 to this guy because it will not be satisfied, and my all resources will exhaust, and all other processes have to actually go into deadlock. So I can't do it. I will say, okay, you're gonna wait it. I go to the next process p1. I'm saying, okay, 1 2 2. Oh yes, I can say, oh, this can finish, right? Now p1 can finish because I have 332. So what I'm gonna do is I will say, okay, I'm not gonna give it to the resource. I'm only chucking, and then I see that if it I can give it, and tomorrow it will come up and it will finish, and it will release whatever the p1 has. Now p1, I see it has 200. This much it has taken. So when it finishes, it release that. So my available, or this time it is in a work, it will increase. So I will have a 200. That means now net I will have 532. Okay, available, right? Now this is finished. Now p1 is finished, so therefore I will make this as true. Now this vector will tell me who is finished or not. Okay, now I can go further. Now this is done. I go further. I go to this guy. Now this guy needs 6 is required for a, so I can't do it because I have only 5. So I go this is I have in a waiting state. I go to the next. In the next I need 1 1, in a b and a c, and a I don't need. So I will say, okay, I can give it. So that means this can finish. When this finishes, this will release whatever the allocation it has. So it will release these. Okay, and I will add them to this. So after p1, the p3 can finish. P3. So this is p0, p1, p2. In this case I have p4 also, which is false. So p3 can finish. This is true. So this is done, this is done. Okay, so I have a sequence that I'm gonna p1, then after that I got a p3. Okay, now this is done. So I what will be work after this finishes? 3, this will be 4, and this is 7. After that I go to the p4. I see 4 3 1. Can this finish? 4 3 1. Yes, this can finish. Now p4 finishes, and it can release whatever it has got. It got 002. So it will release those, and what is net? We got a 5 4 7. This is my net work again. Now I go move on to the p0, which needs 743. I have in hand 745. This can finish. Now p0 can finish. Okay, and I can make it true, and whatever it was holding, it was holding 1b, so that it can release. So 1b it can release. So total I have now 7 5 and 5. Is it? Now I got a 755. Good. Now I can go to this needs 6 guys, so I can simply allocate it. So that means p2 can come in. It will become true. Okay, after done all, after running this safety algorithm, if in this how I will come to know that okay, this is safe. when all the processes can finish in some sequence, whatever the sequence they come in, but they can finish. Okay, so this finish of a vector will tell me if all of these are true. Okay, this is before finish, this is true. Okay, if all of these are true, okay, that means with this this much of resources in hand, I can finish actually. Okay, my process can finish in one way or other way, they can finish. So that means this state is in a safe state. So that means whatever I have allocated, I can allocate that. Okay, but maybe there was a scenario that this guy needed some more, so maybe it needed some 10, and when I come to the here to allocate it, okay, I see the, oh, I can't have. Okay, maybe this also needed 16 a, and I can't have. So that means my if some processes at the end, their finish of I is saying false, then they can't finish with this much of resource, the system is not safe. So I don't allow that request. Does make sense what I'm saying? So that was safety algorithm. What it does, it first whatever is available put in the work and put all the finish of I as false. Okay, then it tried to find an I in this, it will try to find in this matrix some I which has need lesser than whatever is in work. Okay, so it will have, it will try to see, firstly it will try to see finish of I should be false. Okay, it should not, say for example coming back, it should not be true. So it will not now chuck the P of I, because P of I in the first round got true, then it can finish. So finish, firstly the when I'm chucking with some process, its finish of I should be false. That's, I'm not done with that. Okay, one is that thing, that's quite common sense. And second thing is that its need should be lesser than the work. That means it can finish, right? If no such I exists, if there is no such I, then I'm gonna go to the step 4. But if there is some I, then what I do is I will say work is good, work plus allocation, whatever it has allocated, add that to the work what I did here. Okay, and make its finish of I true, make its finish of I true here, and then go to the step 2, back to the 2. Okay, then go to the step 2 and try to find another process whose firstly it should be false here. If that was false, that means it was not, I'm not done with that, and it's whatever its need is, that should be lesser than the work. If it is so, then whatever it has allocated, I will add that to the work. Okay, if it is not, okay, I go further. I'm not gonna go, I'm gonna go to the P3, and then I go to P4 and so on. Okay, and when there is no such I, that means either all of the finishes are true. Okay, everybody's finish is true, so nobody has a finish false, so I can't I can't go further here, or its need is not less than work, its need is more, so I can't allocate resources. So in that case I'm done. Okay, then I come to the 4th point where I see if I will check the finish of I. All the finish of I is true, that means the system is safe. If one of the processes is left out, that means with this resource in hand I can't actually run all the processes. There is no safe sequence. So in that case I'm saying, hey, I got to reverse, because system is not safe. When the system is not safe, I got to reverse this thing. I got to reverse this thing. So I say no, I can't allocate this. This process has to wait. This request can't be granted. Okay. In this case, it was a safe state, because in this sequence processes could have finished. Okay, so if we sum it up, we say if process requests some resources, we first see whether they are in accordance to its need. Then I go to the step 2nd, or that means otherwise there's an error, because you are asking for something more than what you require. And then I see whatever the system has available resources. If your request is in accordance to that, then I can go to the next step. Otherwise I'm gonna wait, because there may be some resources not yet available. See, like this, when we are trying to see there was 7 there, right? whatever it was. I'm saying, 1 second, I'm gonna have a razor, just erase it. I got a 7 here, for example. Then I was saying 743 at that moment. I couldn't give in the beginning. I had the resources 332, okay, available, and my need was 743. I couldn't give it, but that doesn't mean it can't finish, because it got to wait, because later on some process may finish and our available will increase. At that moment it can run, right? That's why we say here that that if your request is not less than available, then you're gonna wait. If it's less than available, we got to go to the next step, right? We got to go to the step third, where actually pretend we have to, because when we allocated, we have to update our data structures. Our allocation is gonna be more, whatever allocated is plus the request. Our availability is going to be lesser than the request, and our need is going to be lesser than the request, because my need is satisfied. But this is only pretension, because before I can really do this, I have to do the safety algorithm. So that's where I have two more data structures, finish vector and a work vector. In the work, I put up the available, what available is, then I will work with the work, okay, and the finish will be all the false in the beginning, and then I will see here I will try to find a particular process which has the finish is false in the beginning, and also it can be its need is lesser than the work. And if it is so, then I will say that this can finish. That means whatever is allocated, I add that to the work, and with that much now in my hand, I will check another process, and so on and so on and so on. And at the end, I will see if all the finish is true. Okay, finish of I is true. If all processes in the finish of I, they are true. Okay, if that what I'm saying is the finish of I is true for all I, that means everything, all of this vector finish is true, okay, then the system is safe. So because like this, we have a safe sequence here, and if we have a safe sequence, that means we can allocate those resources. Our system is safe with this request, so request will be granted. Okay, this is what we saw in that block diagram. I gave it here, right? You request some process request, we apply the banker's algorithm. It pretends it has allocated, then it go for safety algo. If safety algo sees the system is safe, if it is yes, it will allocate that. It will say okay, you can do it. But if it is not safe, it's gonna deny that request. Simple as it is. Okay. So with this, we come to the end of the deadlock avoidance. The next is that we don't do anything upfront. We just let the deadlock occur, and when the deadlock happens, we're gonna detect it. Okay, so we're gonna be detective in our next video. Until then, ma salama. If you are worried about what ma salama means, it actually means goodbye, okay, in Arabic. So ma salama.